Let's talk about how to design an enclosure for your electronics. In this video, I want to cover the items that I have not seen anywhere on YouTube, which is crazy because millions of student projects are doing this, and I guess professionals as well. And it's a tough topic because this is the moment where electronics engineers are trying to be mechanical engineers, and your project is by nature multidisciplinary if you've been asked to make an enclosure and electronics that go in it and software. So when I started editing, I found this video was really long because it's packed with information, but I'm fast forwarding here, and basically the gist of the intro is enclosures are a lot harder than they look because they always happen in multidisciplinary scenarios, and as such you're going to find mistakes that I've made since my degrees are in mechanical engineering and the other elements are self-trained. Your first step is to benchmark. The first step could also be called don't reinvent the wheel. You're going to find appliances for every single item that you need to include in your enclosure, like I need a power input port. Like I need a digital display that's a rectangle so I can press buttons, or something like that. For each one of those, go find an item in your life that has those features and see how it's done. We'll look at some examples right here. For each example that you benchmark, you're going to ask the questions. How did they do it? Why did they do it? And maybe what process was used to make it repeatable. Okay, so this thing, why did they do it? They did it for strain relief. It puts a cushion instead of a sharp edge. This is stamped steel and it has a sharp edge, so they're protecting this cord using that thing. So you can surely buy these off the shelf, and then, okay, now strain relief and elegant covering up of something that may not be painted nicely on that edge, that's handled. I have specific tips for benchmarking. The first one is you're looking for a certain volume. Volume refers to the number of units produced for one specific model. High volume products tend to have a lot of features packed into one or two components, such as a very complicated injection mold shape. Low volume benchmarks are undesirable because we're not sure that they have designed repeatability into all of their components and sourced from suppliers, which can also be discovered by you. Examples of low volume would be one-off prototypes of devices, NASA devices, or seasonal things such as clothes and artistic products like decorations. In the medium volume space, which is essentially where you want to be, the prices will be a little bit higher margin than those things found in department stores, and these products don't have extreme vertical integration, and instead they outsource their modules from vendors that have reliable and accessible, affordable products. Our map for Scuttle Robotics shows vendors for Asia and North America, our preferences, but all of these businesses actually ship worldwide. Today's discussion, we don't want to focus on Amazon and Lazada and consumer-facing businesses, rather the business-to-business offerers such as RS Components. These suppliers will have indexed, mass-produced, very well-characterized parts with data sheets. Like, this is the part of shopping that becomes engineering as well. And you're going to discover things like how common is this shape among connectors, and is there a variation A and B? You'll discover that just by searching through your parts. That means you want to start shopping and engineering at the same time. If you're just a maker, I would recommend shopping Mauser, collecting data, and then go back to Amazon to find equivalent parts. Before you run off and skip this video, yes, I'm talking to an audience that only has access to things like 3D printing and ordinary hand tools. We're not talking about maybe you have a machine shop, but we're going to have workarounds for that. Okay, as far as distributors, these are the ones that I mentioned so far. Mauser is my favorite one when it comes to searching through their catalog and using their catalog to discover information about connectors and interfaces. Okay, and so you're going to discover the ratings for the amperage on connectors. You're going to discover the CAD geometry that you need to work with. And this was going to bring me to this example. Is a super common device that there are many variants of, and the most common also, if you look at the lowest price and then you sort by how many are in stock, that also tells you that it's the most common, and that is a clue that it is also easy to work with and integrate. Okay, so we have a house shape, nearly a rectangle, but this component, if you buy on Mauser instead of Amazon, it will come with a data sheet that has a drawing of this, including the tolerances. Because this distributor, Schurter, by the way, they do have loads of the most common types of interfaces. Their customers are businesses or designers, and so they're looking out for you, not so much for the end user. I mean, and then you get your labels embedded, like this says the ground, and there's a tolerance to this shape. That means I can design this. Of course I can design this shape in CAD, and these are forgiving enough because they have that margin all around them that you can use to plug stuff in. And so if you're plus or minus a little bit, it's all gonna work out, and you can verify this before you even have the parts in your hand. Please search for a distributor that offers a CAD model if you're trying to do something this refined. Now, if you're one level less on refined, then circles are your best friend. Specifically, I'm talking about 12 millimeter circles. If you make an agreement that your stuff will have 12 millimeter ports, then you're gonna find loads of options that have a 12 millimeter fastening arrangement. And so, like, for example, this is a waterproof button, very nice looking, and these are available on Amazon. You can clamp it to a thin wall, and this says, oh, I don't care if your wall is only 1 millimeter or 10 millimeters, I'm gonna let you fasten it in. And then you have a soldering stuff on the other side, okay? And then you can get cheaper ones, and you can also get a lot of the dials have the same configuration. So firstly, you get a guarantee that the geometry is simple to mate this device. Secondly, you get better odds that you already have the tool available to make that feature. You get one more component removed from your breadboard design, and you get a simple connector that you can interface with. And then, okay, now I've got one less feature to design into a 3D print or a bracket. One of the most common power ports on all kinds of household electronics, now this is in the 12 volt range or 5 volt range, is this barrel connector. These are called barrel connectors, and on the back side you've got screw terminals. Okay, forget about whether or not that's there. Now, if we select an option that's gonna pass through a simple hole, that's solved for our enclosure, and we can put it on the front or the back. This aluminum enclosure is called a project box, and they look much more elegant than 3D prints. They're durable and as low as like $15, now available even on Amazon. I strongly recommend them, but you need to consider if you have a wireless communication on your project that you will have to check if it can transmit through the box. And in this example, I simply drilled a hole and then I added a connector adapter so I can put a Wi-Fi antenna. Please disregard my ugly hack job on this end face and consider that you can just 3D print a panel very easily with your precise dimensions for mating components or pass-through components. Another extremely easy way to enclose all of your electronics and even achieve waterproofing is just to slice a piece of PVC, and then you have, for a few dollars, as many copies as you want, and then your design is simplified down to just designing the end caps. In this case, we said, oh, well, if we just use a PVC tube, we know exactly the geometry. If we mess it up, it doesn't take several hours to print, and we're only printing this face. Loads of these components are designed for a certain wall thickness. You can see where it will grab on with its tabs and those small ridges there. Maximum for many components is 2 millimeters, and a 2 millimeter wall can be very floppy on a 3D print. This is why my suggestion is, see, this works out really good because we have a nice rigid assembly. Once you reach 100 millimeters, any wall on 3D printing is going to get floppy. And there's two ways. You can countermeasure that by making the wall thicker, but then you will lose out on loads of really good components that are designed for panel mount. Then the only good solution for 3D printing is to keep this area small. And I would keep your dimensions way under 100 millimeters if you can. Those parts will print better anyway. Imagine when you go very modular, then suddenly you can start just printing one feature at a time instead of measuring 10 times and still getting it wrong. You can use your printer then as a verification of your geometry. Next advice that I'm sure most students won't follow is to design the actual board in CAD before you design your enclosure. And this circuit board, like, if that's too much of a chore, then you are not very fit yet in your practice in CAD. And so either A, it'll take a while and you're going to learn your software, or B, it'll be quick anyway. And then as soon as you start adding 3, 4, 5 components, those clearances become evident in the CAD instead of waiting to prototype every single thing. These are the cable glands that I was referring to, and they're cheap, they're fairly standard, they come in lots of sizes. We have these fingers that give a little rigidity. We have this passage where the wire will feed through, so just look at the right half of this assembly. And then we have this cap, which also, first it would feed on your wire, and then you're going to put the wire through, and this cap compresses those little fingers and causes them to squish that rubber circle down, 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 while maintaining a smooth edge around your wire, thereby giving this waterproof gasket. Inside or outside, that's a design decision. And then you're gonna put this nut on this side. Boom, okay, cable gland. It's a wonderful part. Just remember the keyword gland so you can go find them online. The next thing about benchmarking is that you're going to see about waterproofing. Okay, this is rubber, and so that seems like it might be waterproof, but does my design really need to be waterproof? Probably not. And this is for operating out in the weather, but it still has to have breathability for the sensors inside. I think it has a temperature and barometric pressure. And so almost anything that you're designing does not need to be submersible waterproof. And that is a whole different type of design than just having something generally preventing dust and splash intrusion. So consider the fact that it's really hard to make something fully waterproof. And so if just a bit of water gets into your mechanism, then it can usually survive if it has breathability and you have a chance for that stuff to evaporate. Plus, almost every circuit board will get a little bit warmer than ambient temperature, which helps you cause that evaporation to happen. Find some electronic that you have. Think about how you would handle the water situation and look how they did it. It's usually very thoughtful and easy for you to repeat. This is an example. You can look at the gasket where they've made an intensive effort in order to use such a gasket. If you want to compress this all around the entire perimeter, if this is, let's say, 1 pound to compress these 2 inches, then imagine you're going to have 15 pounds of force all around that border. Can your enclosure withstand 15 pounds of force? Well, in this case, it's a very thick type of casting injection polycarbonate. Polycarbonate is rigid. It's more rigid than all of your 3D printing materials, and they've just reinforced it with ribs everywhere. And so now if you were going to handle that with fasteners, you need way too many. If you want to make your print just 2 or 3 millimeters thick, then you need a screw every couple of centimeters, and then you just start making your design much more heavy. The alternative to this is work your ceiling gasket or O-ring around the other dimension. So this is a dimension where, oh, okay, we're gonna put a groove here and an O-ring and we're gonna cap it off. That requires the designer also to find a way to make sure there's enough force going, oh boy, I can't do this with one. Are you capable to guarantee you have all this force all the time? That's a big design task. And so the alternative is I'm gonna put my groove here around the exterior faces. And all you have to do then is make sure that your shape is convex with no concave zones. And then an O-ring, ordinary O-ring, can be wrapped around it. And then you're gonna make the fitment between, you know, male and female with plenty of space. You can design it, and I bet in only one iteration you can adjust to get the compression that you intended. That is putting the O-ring around the perimeter, and then it's the strength of the material is applying that pressure all the time. When you start diving into compressible materials, then they have durometer ratings. If they don't buy it. And even the Amazon parts do have this. So now you're probably not familiar with the squishiness that you're going to get with durometer. You're going to start trying to calculate everything without any sense of the in-person feeling. So go back, benchmark, find a material that you have become familiar with, and then look up what that is made of, and look up the durometer rating, and then compare that to your O-ring material before you buy it. I think Buna N is a name given to the most common types of O-rings, and they're cheap, durable, withstand acetone and all the other stuff that will attack it'll outlast the other stuff that you're using, so that's good. And then go to McMaster and look up their guides that come with the components. McMaster Car online, they have a catalog. This is a professional, it's a flare just like these ones, but this one's oriented towards hardware and mechanical assemblies. And so if you just search screw or O-ring, at the top of the page it's gonna return a guide that just really breaks down the top, say 8 most common materials that you're about to look through, and it will give you those the general sense of how they compare and why you'd want them. You absolutely must have a flat gasket and a plate-like orientation, then just do this with your scissors and find a roll of silicone material and purchase that. I mean, some of these are like cutting boards, and there's a children's craft. This very thin green one is for like arts and crafts. You can then cut it out. You can trace it very nicely and then cut it precisely, and you'll have the material you need with spare. Grommets are a little bit more friendly than O-rings, and they don't do the same thing, but these will, for instance, give you on a thin wall, it will give you a place to secure and keep a piece of rubber material that hugs your wire, and then you can get assortments very cheaply, and then the two walls on both faces of that will grab the wall of your hole. If you want your stuff to actually work as intended, then for the wires that are interfacing through your holes, you should buy a round insulator type of wire. So this has just two wires in this cable, but now I have a for sure durable outside, and the shape agrees with the passages on the gland or on the grommet. By the way, these aluminum enclosures are called project boxes. That's one of the keywords where you can find these. And they're friendly because they have fairly simple dimensions to work with. And they will probably have CAD models available, so you have part of your project done already. And then you have simple threaded holes on the corner that give you that place to fasten down the end plates. The end plates come with the project box, and then boom, you already have an aluminum that's easy to work with and cut. You can cut these things with just regular hand. In this section, I started to talk about how to handle putting holes in the thin walls of panels, and also the different materials you might select, narrowing that down to fewer options since there are millions. And I'm going to put the holes and the materials, panels, stuff in another video just to keep this video more focused. Okay, for the last section of this video, let me talk about just 3D printing rules of thumb. These are what I use to just get things cranked out and then make adjustments on the second revision, or for special cases, plan otherwise. Mating fitment. I just treat everything to be 0.3 millimeters in deviation from my design. So if I need it to be fitting over a 20 millimeter hoop, that diameter is really two dimensions, top and bottom in the x-axis or what have you, and each one gets 0.3 millimeters clearance from the measurement I took to the design in my CAD. So the diameter on my female part will be 20.6 millimeters in that case. All my mates are more reliable by using that tube because I only need to design 1/2 of every mate in that enclosure. In this example, my only clearance concern is each side of the circuit board, so I add even more than 0.3 on each side. For deboss, you might have a revision number or label, branding, etc. The tip is to use a deboss instead of an emboss. Have it protruding into the material. It usually comes out cleaner that way, and to use at least 0.5 millimeters. I just do everything with 0.5 millimeters and choose a font that has no serifs. Those are the little twiggies at the end of the letters and stuff. This font has rounded edges, so there's not super fine details that are coming through my STL and being trying to be printed by the printer. The font that I always use is DSISO, and then I make it bold. And I always use 6 millimeters in height for the size of that text. And I always use it 6 millimeters up from the base of the print. It's usually not important where it's going to go, but I have a repeatable choice. So that means if my team member is printing, they start to see it. First of all, they start to see the font very early in the print. And secondly, they can notice if the font is not, if it's not upright, that means we are not printing in the same direction that the print was intended, the design was intended to be printed. So it's an indicator to tell us, just because I do this all the time, I don't have to think about it, and it helps catch mistakes downstream. Agree with the Z-axis. Yes, so the font is pointed upright. Draft angles, I just do generally things starting with 2 degrees if I don't have some other criteria to meet. It's fairly conservative, usually stamped items. This is a deep drawn stamped metal, and also the injection cast items, they also will usually have a 2 degrees or less if they're trying to get this parallel wall. But if you just start with 2 because you don't feel like trying to measure the inside base of this. By the way, the wall thickness is not consistent for a deep drawn part, so that if I measure the outside, it's not going to give me the same accurate information. The wall thickness on a deep drawn part is not consistent all the way around, so I cannot just measure the outside and then subtract the thickness of the walls. Because it's okay if I clear it with extra margin, extra space. All right, clamping rings. We have very often somebody will want to clamp a part onto a rod. And to do this, it happens so frequently that I just gave myself a criteria that I start with. 270 degrees is how big I'll make the circle. So that means 180 degrees would be, this gets cut off here and here. And of course it would clear and fit right on. And 270 says, okay, now I'm going to have that stretch a little bit in order to pass onto the rod. Okay, now I have a way to secure my item. By the way, this blue guy was not designed for the gray pipe. It's for another pipe, and you would not see this. That big gap says I'm not even making contact most around. Instead of, don't try to achieve compliance by changing your diameter. Make your diameter match your mating part, and then maybe reduce it just a hair, just to deal with this 0.3 millimeters or so. So they generally agree. I said with compliance we're going to 170 degrees, and I'm generally making this wall at least 2 millimeters, but not much larger, because then we're going to stress. If this was twice as thick, just stretching it would tear at the inside edge of that hoop. Flexibility is a function of the cross section, and that is the area moment of inertia. Oh boy. But anyway, you treat this as a beam, and you make your beam thin, not rigid like an I-beam would be, looking at this rectangle here, for compliance, thin. And again, just go to benchmark, because you don't need to calculate all that stuff. You can just see what other plastic designers have done. Without compliance, we're starting, I'm just throwing that out there, 190. I don't have a criteria, but at least somewhere to start if you're wanting to do this. Like, imagine this is a full solid part where the gap in my hand is all solid plastic, and I want to fit that on there. Now I don't have a compliance in my geometry, I just have a compliance of the material itself, and that might even be too tight. Okay, wall thickness. Rule of thumb is 2.4 millimeters. That's where 2.4 millimeters gives you rigidity in your parts, and it is a multiple of my path width in the slicer once I've imported the model from an STL file. This thickness also allows for me to put a deboss in the wall for labels without ruining the integrity of that wall. It holds up even if I have a minor defect in the printing, but it is still thin enough to accommodate most off-the-shelf panel mount, buttons, etc. With all of that said, you still have to make sure that your slicer is not putting a void in between the exterior faces, such that you would lose about 50% of your strength. The wall needs to be bonded. Loads of these components are designed for a certain wall thickness. You can see where it will grab on with its tabs and those small ridges there. Maximum for many components is 2 millimeters, and a 2 millimeter wall can be very floppy on a 3D print. This is why my suggestion is, see, this works out really good because we have a nice rigid assembly. Once you reach 100 millimeters, any wall on 3D printing is gonna get floppy. And there's two ways. You can countermeasure that by making the wall thicker, but then you will lose out on loads of really good components that are designed for panel mount. Then the only good solution for 3D printing is to keep this area small. And I would keep your dimensions way under 100 millimeters if you can. Those parts will print better anyway. Holes, vertical holes, maximum of 6 millimeters. Basically vertical features, you can survive 6 millimeters. It doesn't seem like an overhang to that plastic if you're 6 millimeters or less. It's just like a continuous feature. I don't know how to say it, but you don't have to countermeasure overhangs that are small and up to 6 millimeters, except when you need precision. Then you could still get away with that and then just drill it out afterwards. All right, base chamfer. I just always apply a chamfer on the base of every print pretty much, so that will avoid elephant's foot if your printer isn't tuned in perfectly, and it also just gives you a much more professional looking result. I usually do top and bottom chamfer at pretty much at the very end. That's the last feature in my feature tree. So the design fillets go in first. So this corner and this corner have a fillet. When I do that before the chamfer, then the chamfer, it's just one chamfer and it just sweeps all along. And that chamfer is, since I always use a small value, it's smaller than most of my fillets, so it doesn't break the model or create any wall seams by having it nice and thin. If you don't need a chamfer for your appearance, it still helps make sure you don't have burrs and hang-ups on any edges. Threads, I don't print threads into parts unless we're talking very large. Ooh, benchmarking saves the day once again. All around you'll find products where the threads are involved and you have like say a cap to the soap or a cap to any different plastic product, shampoos and things. And those molds have threads designed into them, and those are always like this big or larger. Well, maybe smaller ones, but you will not find products where a small screw hole has threads printed into it in the mold. It's too small, and then your strength does not have an agreement. Sorry, let me finish this and then I'll talk about strength. Strength is important. Geometry matching, working with the tolerances we have on 3D printers. Okay, big stuff, easy. And the sealing, we're not achieving sealing by perfectly matching this thread. We're achieving sealing by having a gasket. And then, exact same thing. On the top of the bottle of your soy sauce or something, there will be a gasket. It's a thin, squishy plastic. And another reason to use ABS, you can do this, just wipe it with acetone, or you can do a whole full-blown acetone vapor bath. You can check YouTube for other videos on how to do it, but with ABS, you can totally seal up your part if you want to and get a result that's shiny. Okay, screw strength and sizes. I just make designs with 2 sizes of screws for my own simplicity and the inventory on the shelf, and that is the M2.5, that's metric, 2.5 millimeters, or M6, and then deviate if something calls for it. But look at this brass insert is what people use in actual injection molded parts, as well as in 3D prints. You stick that thing on a soldering iron and you poke it into a pre-existing hole. So that's a 2.5 millimeter screw in diameter. We make a 4 millimeter hole, and then that's in the print, and then we poke that into the hole with some heat, and it's pretty easy to do. Alignment varies very slightly, but it never causes a problem if you have just a panel that your screw is passing through. The hole in the panel clearance, again, that would be like 2.8 millimeters or so is the designed hole size for this to pass through without interfering. This screw, 6 millimeter diameter, it will carry over 600 pounds in tension. So if you have this in an assembly and then you pulled on it, 600 pounds of force to pull that and break it. So obviously there is no piece of plastic that's going to engage and survive that amount of force, and that means we're not choosing our screw size for the strength of the screw. We're handling it for the ease of assembly, affordability, the geometry of everything we're working with, and we wouldn't print threads because even if the geometry was easy to get a good result in printing, it's still, the plastic is not strong enough. So in small screws, if you need a small force, then you're going to use a self-tapping screw. If you need a larger force, you will use some sort of insert or an actual nut, a piece of metal hardware on the other side. And if you need a larger force than that small M2.5 can provide you with, then you go up to M6, but you are still using metal hardware to mate with the screw. All right. On any of the small screw sizes, you can benchmark, and they will either have something like this involved in the actual assembly, or they will just use a screw that is self-tapping. Self-tapping or thread forming is the two terms that you will find as keywords for searching for this type of screw. They have much more coarse threads. They only take a few turns of the wrist when you're assembling, and these will engage, cut into the plastic, and fit themselves nicely. Again, when you order the stuff, you hop onto McMaster and see the screw, the hole size intended to, it doesn't matter where you are in the world, it doesn't matter if you're ordering from McMaster, they have a beautiful data that comes with their screws that says, what's the hole size intended for that? Okay, I'm gonna wrap it up there for this video. The topic was how to design an enclosure, maybe using 3D prints, but in general, design an enclosure for prototyping with electronics. And I'm sure I've made mistakes and fell short of every key topic, but I did think that I covered 90% of the blaring errors / difficulties faced by students that I see in the undergraduate spaces and graduate spaces. So if you follow all that advice, save this video for when you're ready to implement and then maybe review. I'll make the chapters so that you can just hop back to the most relevant parts for you. And also happy to hear feedback and improvements on any mistakes that I made. Hope everyone has a great day.